Hello everyone, I'm Dr. Nitish and welcome to Intuition. Today is the first milestone on the road to relativity. It's history. Because knowing how this theory came into being is very important for understanding what it is about. And secondly, the circumstances around its inception have shaped it in a particular way. It could have been very different otherwise. Most of the content on relativity starts with Galileo's proposal that someone in the basement of a ship, without looking outside, cannot know whether the ship is stationary or moving at a constant speed. Because everything will look exactly as on land. This is from his 1632 book, Dialogue Concerning the Two Chief World Systems. But what made him write this? The answer to that lies in ancient history. Around 200 BC, when Aristarchus presented the first known heliocentric model that placed the sun at the center of the universe, with the earth rotating around it. He was supporting the theory of Anaxagoras, who lived even before him, according to whom the sun was just another star. This was way ahead of its time. So far ahead that even after 350 years, around 150 AD, Ptolemy proposed the geocentric model with the Earth at the center of the universe. And it remained the dominant theory till the year 1510. For more than 13 centuries, it had major issues with observations of the planet's motions, but ad hoc explanations like planetary epicycles were invented to support it. It somehow worked, though it kept getting harder and harder to continue with it. Then in 1510, Copernicus proposed the heliocentric model. Again, it explained every issue, which the truth usually does, but still, it was hotly debated for the next 122 years, because of which Galileo had to write that book about the two world systems. The two systems are the heliocentric and geocentric model. But why was it so difficult to accept the heliocentric model? Remember, it was first proposed before 200 BC. There were people intuitive enough to fathom this idea even then. Some say it was against religion to accept that the earth wasn't the center of the universe, that it wasn't God's greatest creation. Another view is that it is hard for the human ego, but though the church was definitely against it, it wasn't the only opponent. There were great scientists and philosophers who couldn't accept it for centuries, even in the face of overwhelming evidence. Even when it explained everything so elegantly, they could have at least accepted the Earth's rotation. It explains the sun's, moon's, planets, stars' motion in the sky to a large extent, and any discrepancies could be explained by them doing their own little personal motions. The Earth could still be at the center of the universe. The church and human ego could keep their peace, but it wasn't accepted because of a much deeper issue. It was unthinkable that the earth could be moving, even rotating, without any noticeable effect. Even Ptolemy had refuted this idea, saying that a rotating earth would cause very strong winds in the opposite direction because the atmosphere would not move with the earth. And the philosophers after Copernicus asked, if we throw a ball straight up, why does it fall back in our hands? Didn't the earth move through space when the ball was in the air? To be fair, let's imagine those times. Nobody had experienced smooth motion like a train or a plane. Movement felt completely different from rest, the way it does when the only movement you have experienced is riding a horse or being on a boat. It was unimaginable that the earth could be moving through space imperceptibly. And it was this argument that Galileo was refuting. He was proposing that only the movement relative to other material things can be perceived, not relative to space. This is the essence of Galilean relativity. The obvious deduction from this relativity is that speeds add or subtract like regular numbers. If A sees B moving at 5 km per hour towards some direction, and B throws a ball at 5 km per hour according to B in the same direction, A will see the ball moving at 10 km per hour. It feels natural, right? But let us look at it from another angle. If A sees B moving at 5 km per hour and this ball moving at 10 km per hour in the same direction, he can assume that B sees it moving at 5 km per hour. And by the way, this kind of speed addition is called Galilean transformation. This velocity addition rule is so intuitive that nobody questioned it. Nobody thought of verifying it by experiment. It was automatically believed to hold true for all velocities. 1 plus 1 is 2 and 1 million plus 1 million is 2 million. And this addition directly follows from the first rule, because neither 1 nor 1 million is special. All are relative velocities. These two rules became very well accepted, natural, instinctive, obvious properties of our universe. And then came Newton with his mechanics. The relationship between force, acceleration, velocity, momentum and energy. And all these are derived from his second law, F is equal to ma. The direct implication of Newton's second law plus Galilean relativity is that force and acceleration are proportional at all velocities, because no velocity is special. A force will cause the same acceleration irrespective of the speed of the object. If your spaceship's rockets are firing and providing a thrust that gives an acceleration of 1 meter per second, you will go from 0 to 1 in 1 second and a million to a million plus also in 1 second. And there is no limit to the speed you can achieve. This Galilean relativity and Newtonian mechanics are logical, simple and intuitive. Nobody felt the need to question them. Though, to be honest, there were no means to experimentally test them too. But we should always remember the lack of an experimental foundation under this obvious structure. Oh yes, Newton did one more thing. He defined space like this. Absolute space in its own nature, without regard to anything external, remains always similar and immovable. And he stated this about gravity. You can pause and read it. In these two and many other statements, Newton characterized space as just nothingness, the absence of matter, an inert background that has no effect on matter, having no property whatsoever. Gravity too was an effect of matter on another matter at a distance, with no part played by the intervening space. Oh yes, one more thing. He described light as made of particles, emitted from a shining body and traveling to another body, without requiring any participation by the intervening space. And in this way, Newton stripped space of any significance. So this was Newtonian physics, which nobody questioned for 2 centuries. Then in the early 1800s, among a lot of other things, Michael Faraday saw lines of force around a magnet, which can be easily seen if you sprinkle some iron filings near a magnet. And this shows that something obviously non-material is present around a magnet. What I mean by non-material is that its presence can be detected only by its effect on matter. But Newton's shadow loomed so large over the physics of that time that the idea of space having any property was sacrilege. Faraday's contemporaries, among them Ampere, were Newtonians. They just could not believe that space could have anything to do with anything. And also Faraday had no training in math, though he was a brilliant experimentalist. He could not develop a formal mathematical framework of these lines of force, where Newton's legacy was of mathematical formalism. If the theory was not in equations form, it wouldn't be taken seriously. It took half a century for Maxwell to come and form equations of the electromagnetic field. And these equations played a pivotal role in the development of relativity. From here on, I will not go into details because most of the stuff will be covered in separate videos. So Maxwell's equations had 3 features. First, these were based on electric and magnetic fields by which a magnet or a charge acts. Secondly, in his equations, there were 2 different fields, electric and magnetic. Moving a magnet near a coil of wire was conceptually different from moving the coil near the magnet, because both were acting on different fields, but both movements caused exactly equal amount of current in the wire. So somehow the 2 fields were fundamentally one. Thirdly, he found a wave speed within his equations, a wave related to electricity and magnetism. And that wave speed was equal to the already measured speed of light. He realized that light was also an electromagnetic wave. Perhaps the first person to have realized that. But that wave speed is relative to what? The answer was obvious to everyone. It was the medium of the wave. Of course. They called that medium ether. Now, every physicist worth his salt wanted to measure his speed relative to this ether, because that would be a kind of absolute speed. Nobody after Newton had thought it was possible. So two scientists, Michelson and Morley, designed an experiment to measure the velocity of Earth relative to this ether, as Earth was the fastest moving object known at that time. Their experiment would notice a change in light speed due to the motion of Earth through ether. They found no change. And this made no sense. We would have a video on this. So Lorentz and Fitzgerald tried to make sense of it by mathematical adjustments. Lorentz justified the math by proposing that movement through the ether contracts things in such a way that detecting the motion is impossible. This led to a way of adding velocities, which is called Lorentz transformations. And here Lorentz was letting go of Galilean transformation but trying to save the concept of ether. He was saying that everything does move relative to ether, but that movement remained undetected. Then came Einstein. He made sense of that math by introducing his theory of relativity in 1905. He basically proposed that there is no ether, no need for it. Instead of length contraction, time slows down. This mechanism needs no ether. And that magnet and coil issue of Maxwell, only the relative movement of the magnet and coil matters. They are acting at each other through an abstract field which is very unlike material ether. So Einstein stripped motion through space of all significance. Again, Minkowski in 1907 made the theory completely mathematical, in fact geometrical, by introducing space-time, an abstract four-dimensional entity populated by four-dimensional events, not just three-dimensional beings and things. Einstein didn't like this. But this reduction of relativity to equations helped Einstein later in developing the general theory of relativity. And here is the greatest irony. General relativity is in a way a U-turn. Space, which was deemed irrelevant in special relativity, became the seat of gravitation. And yes, Lorentz never let go of the idea of ether. And Einstein later admitted that some kind of ether is there in a 1920 lecture. And this is an outline of the history. Relativity appears to be about the constant speed of light. But the core idea is the effect of motion through space. Whether space is just an inconsequential nothingness or is it a stage that affects its actors fundamentally. That is what relativity is all about. A particular property of space. We will see how it makes length contraction, time dilation and mass energy equivalence and clears up the impossibility of a faster than light and time travel. And also it resolves the biggest paradox of all, the twin paradox. Subscribe, share, like and join us in the next video about the Michelson Morley experiment, also called MMX. Take care.